Have you ever wondered how fast light travels, or how we even measured its speed? These are questions that have intrigued humans for centuries, prompting countless experiments and theories. Light, a fundamental constant of the universe, zips along at an astounding speed of approximately 299,792,458 meters per second when in a vacuum. But how did we arrive at this figure? The answer lies in a fascinating journey of discovery that traverses the realms of physics, astronomy, and even quantum mechanics. This journey has reshaped our understanding of the universe, underscored the genius of minds like Ola Romer and Albert Einstein, and unveiled phenomena like Cherenkov radiation and the role of light in quantum electrodynamics. It's a journey that continues even today, with recent advancements pushing the boundaries of precision in measuring light speed. So, join us as we unravel the fascinating journey of how we've come to understand the speed of light. The quest to measure the speed of light began several centuries ago. With these words, we dive into the fascinating history of how humanity first began to gauge the speed of one of nature's most mysterious phenomena: light. Our story begins in the late 17th century with Danish astronomer Ole Romer. Romer made a groundbreaking observation while studying the moons of Jupiter. He noticed that the time taken by one of Jupiter's moons, Io, to circle its planet, varied depending on Earth's position relative to Jupiter. From this, Romer made the audacious deduction that light must have a finite speed. He estimated it to be around 200,000 kilometers per second. Not quite on the mark, but a monumental first step nonetheless. Fast forward to the 19th century, and enter Albert A. Michelson, an American physicist. Michelson was not satisfied with the rough estimates of his predecessors and set out to measure the speed of light with greater precision. He ingeniously used a rapidly rotating octagonal mirror and a beam of light reflected over a long distance. Through a series of such experiments, Michelson refined the speed of light to a much more accurate figure of about 299,792 kilometers per second. Michelson's work earned him the 1907 Nobel Prize in Physics, making him the first American to receive a Nobel in the sciences. His precise value for the speed of light has stood the test of time, with only minor adjustments made thanks to modern technologies. From Romer's daring theory in the 17th century to Michelson's meticulous experiments in the 19th, the journey to measure the speed of light is a testament to human curiosity and ingenuity. These initial measurements paved the way for a deeper understanding of light and its behavior. They set the stage for the revolutionary ideas that would emerge in the 20th century, forever transforming our perception of the universe and our place within it. Indeed, these initial measurements paved the way for a deeper understanding of light and its behavior. Enter Albert Einstein, a man whose name is synonymous with genius. In the early 20th century, this patent clerk turned physicist introduced a radical idea that would forever change our understanding of the universe, and of course, the speed of light. This was the theory of special relativity. At its core, the theory of special relativity revolves around one simple yet profound postulate. The speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the source of light. Now let's take a moment to unpack this. Imagine you're standing still, watching a car speed past you. The car's speed is relative to you, the observer. If you started running alongside the car, to you, it would appear as if the car is moving slower. But this isn't the case with light. Whether you're standing still or chasing a beam of light at breakneck speeds, light always travels at an unfaltering speed of approximately 299,792,458 meters per second. This constant speed of light, coupled with the idea that the laws of physics are the same for all non-accelerating observers, forms the crux of Einstein's theory. But what does this imply? Well, it leads to some mind-bending conclusions. Time, for instance, is not absolute. It can stretch and squeeze, slow down and speed up, depending on how fast you're moving relative to something else. This concept is known as time dilation. Likewise, space is not fixed either. It can contract or expand, a phenomenon we call length contraction. So, in essence, Einstein's theory of special relativity tells us that space and time are interwoven into a four-dimensional fabric known as spacetime. Einstein's theory challenged and enhanced our understanding of not just light, but the very fabric of the universe. It taught us that the universe is a strange and wonderful place, where time can stretch, space can squish, and the speed of light remains the only constant. Light doesn't just illuminate our world, it sets the cosmic speed limit. Imagine the universe as an immense cosmic racetrack, In this grand race, light is the unrivaled champion, sprinting through the vacuum of space at a staggering speed of approximately 300,000 kilometers per second. According to the laws of physics, as we currently understand them, this speed is the ultimate limit. Nothing can travel faster. This speed limit isn't just for matter, it applies to information as well. If you were to wave a magic wand and instantly move a star billions of light years away, we wouldn't notice the star's absence until its last light, emitted before your trick, finished its journey to us. This is because the information of the star's disappearance can't travel faster than light itself. So, in the universe's grand racetrack, nothing can overtake light. Now let's delve into the quantum world, where the speed of light plays a significant role. Quantum electrodynamics, or QED, is the quantum theory of light and matter interactions. It's a fascinating field that's all about explaining how light and matter interact, and guess what's at its heart? Yes, you guessed it right, the speed of light. In this framework, photons, the particles that make up light, zip around at the speed of light, which is approximately 299,792,458 meters per second. Quite a mouthful, isn't it? But it's this constant speed that shapes our understanding of the universe at the quantum level. Photons are intriguing creatures. They have no mass and yet they carry energy and momentum, and because they're massless, they're always on the move, never at rest, always at the speed of light. This is one of the cornerstones of QED. But here's where it gets even more fascinating. In the quantum realm, light doesn't just travel in straight lines. Photons can take multiple paths from point A to point B. They can even take a detour around the moon if they wanted to. This is what's known as the principle of least action, and it's one of the key concepts in QED. But wait, there's more. The speed of light also plays a crucial role in the uncertainty principle, one of the fundamental aspects of quantum mechanics. This principle states that you can't know both the position and momentum of a particle with absolute certainty. And since light is made up of particles, the photons, the speed of light is inherently tangled up in this uncertainty. So you see, the speed of light isn't just about how fast light travels, it's a fundamental part of our understanding of the universe, from the macroscopic observations of relativity to the microscopic interactions in the quantum world. In the quantum realm, light continues to baffle and astound us. Science never rests. Our understanding and measurement of the speed of light continue to evolve. As we journey into the 21st century, our quest for precision has led to the development of modern techniques and experiments for measuring the speed of light. One such method, known as the cavity resonance method, involves creating a resonance within a cavity filled with a medium whose refractive index is known. This technique has been used to measure the speed of light with an astonishing degree of accuracy, to within a few parts in 10 billion to be precise. Another fascinating development is the use of femtosecond frequency combs. These are laser-based tools that produce a spectrum of light that resembles the teeth of a comb. By comparing the frequency of this spectrum with the speed of light, scientists have been able to measure light speed with unprecedented precision. And then there's the phase comparison method. This technique uses two lasers of slightly different frequencies. These lasers interfere with each other, creating a beat frequency. By measuring this beat frequency, along with the frequencies of the lasers, we can determine the speed of light. Not to forget, the time of flight technique. Here, a light pulse is sent from a source to a target and back. The time taken for this round trip is measured and used to calculate the speed of light. This method, while not as precise as others, is nonetheless highly useful in practical applications, such as in the field of telecommunications. These advancements not only reflect our growing understanding of light speed but also our relentless pursuit of knowledge. With every step we take, we refine our measurements, we question our assumptions, and we push the boundaries of what is known. As we continue to innovate and experiment, we are constantly reminded that the quest for knowledge is a journey, not a destination. Each new discovery, each leap in understanding, brings us closer to unraveling the mysteries of the universe. As we continue to refine our understanding, who knows what future revelations the speed of light may bring?